It's been more than 3 months since I installed a lithium iron phosphate battery into this Suzuki SV1000, and I'm pretty happy with the results. I've been riding it not that much, probably 5 to 7 times, but it's worked great so far for me, and it's winter right now. It's a pretty mild winter though here in Seattle. You know, it rarely gets below 36 degrees Fahrenheit or a couple of degrees Celsius. So I'd like to show you today what I have, how I wired it up, and explain why I made the choices that I have made. Let me put the camera on the other side. This is the battery compartment of my Suzuki, and as you can see, I took the old battery out, and underneath this foam here there is a 8.4 amp hours lithium iron 4-cell lithium iron phosphate battery. So this guy here, I bought it from Hobbyking. It says 8.4 amp hours, 4 cells in series, 2 cells in parallel, total of 8.4 amp hours at 13.2 volts. It weighs 1 kilo, which is much less than the stock lead acid battery. On top of the battery itself, I have this BMS, and I'll go into a little bit more details why I have decided to go with this BMS. But just to explain the wiring a little bit, these two black and red wires are the thick current carrying wires that come from the battery. These are 8 gauge silicon wires, and this guy here is a balancing lead that comes from the battery. So the balancing lead goes off, and once it splits in two. One side goes into the BMS to balance the cells, the other one goes back there in a compartment that I can open just with my motorcycle key. This is for debugging purposes, just for monitoring and such. It actually proved to be very helpful, that external balancing lead. It allowed me to find a problem with my cells. So I decided to hook up the positive terminal from the battery directly to the motorcycle here. So this is the red side of the battery. I soldered a connector here. I have a copper spade connector here that goes to the battery clamps on the motorcycle, and then it continues there. The negative side goes through the BMS. So the negative side goes into the B minus here on the BMS, goes through all these MOSFETs, and then goes to the negative side of the motorcycle. Let me start this thing up just to show you how it operates. So this is a cold start. I didn't start it today. It's not that cold today, but I just want to show you, because lithium iron phosphate batteries are a little bit worse in cold weather. Before they can operate well, they need to warm up a little bit. So this is without the warm up. As you can see, it has no trouble at all starting the motorcycle. I actually feel that it's a bit better than the stock lead acid battery that I used to have here. You know, at least in my opinion, it has more grunts. It sounds better when it starts, and the headlights don't go as dim as they used to go on with the stock lead acid battery. I'd like to do some measurements for you to see how long the voltage sags on the battery when it's under when I start this thing. For that I'll need to hook it up a little bit. Just give me a second. So here you can see my fluke multimeter, and it's hooked up to this balance lead. So I just hook up to the topmost and bottommost terminals on the balance lead. the balance lead goes directly to the battery, and the balance lead itself doesn't carry any current. So the voltage that will be here is pretty much the voltage at the terminals of the cells themselves, as close as I can get to the battery. Let's start the fluke. Let's make it record. So now the voltage is 13.3, and the 13.3 on the lithium iron phosphate battery is actually a full battery. When this battery is at 100%, it has 3.33 volts per cell times 4 gives you about 31. Okay, now I'll start the motorcycle, and we'll see how low the voltage drops on the battery itself. This motorcycle has an injection system, and now the headlights are on, so you can see there is a little bit of voltage drop even now when I started. So that the motorcycle goes on to charge the battery right away. So here the minimum voltage on the battery is 8.92 volts. So we see quite a bit of sag in the voltage of the battery, and it's actually going to get worse because this doesn't take into account the wiring that I did here, and it doesn't take into account the BMS. So this is on the battery directly. But actually, well, the wiring, the lower the voltage on the battery can go, because a good wiring will deliver more power to the motorcycle. So let's measure what the motorcycle actually sees. So I'm gonna unhook these two guys and get this on the other side. Negative to negative. Positive here. So yeah, because I started the motorcycle the previous time, you can see the voltage is a little bit lower there. Let's see it again in action. Oh, let me start to record. Injector going there. Now it's ready. And it's starting. 8.6 volts. Well, actually, that's pretty good. In my previous experiments, what I've seen happening is that I've seen that the difference between the battery voltage and the voltage seen by the motorcycle after all the wiring was about 1 volt. In this particular experiment, we have seen not as much of a difference, but some of that may be due to the fact that this multimeter can measure the voltage once every 100 milliseconds, so it can miss the spike in the beginning of the starting, the biggest spike. So you know, these measurements should be taken with a grain of salt. And also I wanted to point out that, you know, here I have exposed wires from the battery themselves through the balance lead. Be very, very careful with that, because if you accidentally short these two wires, the battery is so powerful it can burn through those wires with zero effort. So let's go to the bench, and I'll explain how I reached this setup and why I have decided to make it the way I made it so far. The reason why I decided to go with the lithium iron phosphate battery is that my lead acid battery on the motorcycle died, and the last lead acid battery that died was the third one on this motorcycle. So the stock one actually was pretty good. It lasted for about 10 years, but it died unexpectedly pretty much on the road. Just the motorcycle stopped, and then when I tried to start it, it had no juice whatsoever. You know, I suspected some electrical system malfunction, because I didn't expect the battery just to die. like that. But when I got home, the battery just wouldn't hold the voltage whatsoever. So I installed another battery purchased from a local dealership, and it was a decent battery. I paid like $60 or $80 for it, and it stopped working after about a year. And I suspect that I know the reason why it stopped working. I was hooking up a trickle charger on it because I don't ride the motorcycle as often, and I kind of wanted to keep the battery fresh. Lead acid batteries like to be fully charged, so I was putting on the trickle charger while I didn't ride, and I suspect that the trickle charger was the one that killed the battery, because after the first replacement battery died, I purchased a second one from Amazon, and it was a expensive one. I don't know how good that was. Paid around $100 for it, and it died as well after about a year. So I said I'm fed up with the lead acid batteries, and I decided to go with the lithium iron phosphate battery. So the first lithium iron phosphate battery that I found was this one, and I found it on Walmart website pretty much by accident. I actually didn't know that one could install lithium iron phosphate batteries on a motorcycle or on a car for that matter. But it turns out that 4-cell lithium iron phosphate has a voltage range which is very similar to the lead acid battery, which makes with the 6-cell lead acid battery, which makes them voltage compatible, and it's very nice. I find it fascinating that such a coincidence allowed us to pretty much have new type of battery in old hardware. Lithium iron phosphate chemistry is such that the battery itself is full when the cell voltage is 3.3, about 3.3 volts. So if you multiply it by 4, you get 13.2 volts, which are written somewhere in here. Maybe not. 13.2 is the full battery voltage, and this is a little bit higher than the full lead acid battery. Full lead acid battery is 12.6 volts, but because lead acid batteries are quite happy with being somewhat overcharged, up to 13.6 volts. If you put on a lead acid battery pretty much continuously, it will not evaporate the liquid, the electrolyte from there, because it will be able to recombine and it won't vent. So usually what the alternators and the chargers do, they actually supply a voltage higher than 12.6, and it depends on the charger. I've seen anywhere between 13.6 and 14.6 for the bulk charge. And the beauty of the lithium iron phosphate battery is that it actually will tolerate 14.6 volts. Lithium iron phosphate chemistry is pretty reliable, and a cell voltage can go up to 3.65. If you multiply it by 4, you get 14.6 without damage. So this was the first battery, and the price is actually pretty good. $100 for a replacement battery, which will be much lighter than my lead acid battery. I was seriously considering buying this option, but then I looked online to see. I looked at the comments, and some of the comments were pretty bad. So what people were saying is that they say that this is 10-14 amp hour battery, lead acid equivalent, and lead acid equivalent is a marketing gimmick that these guys came up with. Not these guys, but all the guys who sell lithium iron phosphate batteries. They came up with just for people to allow to compare the batteries, but this battery actually doesn't have neither 10 or 14 amp hours. From the comments, people say that it's actually a 4 amp hour battery inside there, but it's rated for 240 cranking amps. So it should be able to start my Suzuki there, no problems. So I went to see what other batteries are there and what people have to say about them. and the best ones seem to be these Shorai batteries. But for a battery that will suit my SV1000, the Shorai website recommends, well, this particular model, and it costs $230. And $230 is actually more than I wanted to spend on a battery for my motorcycle. So I looked it up and I tried to, and this, apparently this is a 21 amp hour lead acid equivalent, and my stock battery was 14 amp hours, so I think this is actually too much. And it has, I believe it has 315 cranking amps, and my manual says that I need 200 cranking amps, so I said that you know, I can go a little bit lower than that. But even the lower version, which has 18 amp hour lead acid equivalent for the SV650, that can deliver 270 cranking amps, it's still $190. So I mean, what I had to choose from was this battery, I guess, or the battery tender one. And I didn't, I mean, battery tender doesn't look trustworthy to me. This one looks trustworthy. At least people have good things to say about it, and there are some experiments that people do online with these batteries, but the price was too high. So I went to my favorite hobby website, hobbyking.com, and I found this guy here. So this is the 4 amp hours lithium iron phosphate battery that's able to deliver 30C constant and 40C burst, which translates to 126 amps constant discharge and 168 burst current. And you know, this is a hobby battery, and when they say that they can deliver 30C constant, 126 amps constant, it really can. I mean, I really trust that it can, unlike the battery tender, which say 240 cranking amps, and cranking amps is like the absolute maximum or something. It, you know, I have serious doubts that that this battery will be able to deliver 100 amps constant discharge rate. So, but because this, even the burst is lower than what is recommended for my motorcycle, I decided. So I think these two, I think the battery tender and this one are pretty much equivalent, but I didn't want to stress this battery too much, so I decided to go with the higher version, the next model up, which is 8 amp hour battery, and it can deliver the same 30C and 40C burst, but this time, because the capacity is higher, it translates to 150 to 330 amps in burst, which should be more than enough to start my motorcycle. It costs $82, and that's about the price that I paid, probably $6 shipping I paid, so around $90 for this battery. And I'm pretty happy with it. It's, you know, it's a little bit more heavy than the other one. It weighs about 1 kilo, and the other one is half of that. But I think, you know, this one will be pretty reliable. So in all my naivety, I was just planning to hook this battery up to my motorcycle as is, you know, red wire to red wire, black wire to black wire. What can possibly go wrong? You know, but there is a difference between the lead acid batteries and the lithium iron phosphate battery, which is pretty significant in this case. And the difference is that if that lithium iron phosphate batteries, they don't allow you to overcharge it. I mean, it will burst into flames. Well, lithium iron phosphate will not burst into flames. The lithium ion will burst into flames. Lithium iron phosphate will not be happy anyway if you overcharge it. With the lead acid, you can put 10% more voltage than the full battery, and it will be okay. It will just, you know, translate into heat. It will the electrolyte will split into hydrogen, oxygen, and then recombine back inside the battery. Nothing bad will happen, and that's how they achieve balancing the cells. So if one of the 6 cells in the lead acid batteries is more discharged than the other ones, they will overcharge all the other ones to bring the discharge one up to the level. And and it's pretty much self-balancing. The lithium iron phosphate batteries are not like that. This is why they need a balancing circuit. So first, my first plan was to just use a simple, hook the red and black directly to the motorcycle, but then use a balancing circuit like this, or something similar that I purchased from eBay. So you hook this guy up into the balancing lead there, and what this thing does is that if a cell reaches 3.65 volts, it starts to discharge that particular cell through the resistor there. So it has 4 resistors and four circuits for every cell. Or there is another one. This is actually a bigger one. So they're about $5 each. I bought 2 of them just in case. And it does work. I tested it. I put 3.4 volts and stuff. Just a second. I put 3.4 volts in there, and it was drawing no current, and at 3.65 volts it started to discharge. But the discharge rate for this thing is pretty low. So if your battery is really out of balance, then these things will not be able to keep up. Like, they will try to discharge the cell that is overcharged, but if the motorcycle puts more current than this thing can draw, you will damage your cell. And that's one thing. And the other thing that was very concerning to me is that lithium iron phosphate batteries, they don't like to be discharged completely. So if I were to ever forget the motorcycle with ignition on for a couple of hours, it would discharge my battery, and then the problem would be that I wouldn't be able to go, because even if I jump start the motorcycle, the battery is not safe to be charged anymore. So I'd have to get myself a new battery before I can ride the motorcycle again. And it's one thing, it would kill the battery, but the likelihood of that is pretty low. I'm pretty diligent turning my motorcycle off, but the additional trouble of having to find a new battery before I can move the motorcycle, just because of that I decided to go with a full-blown BMS. And this is a example listing of the BMS that I got. I got actually 2 of them. One I got from eBay and the other one from AliExpress, and I'll tell you a little bit more details. But before that, I wanted to show you some specs for this BMS. So the BMS is there to do several things. One, it has a balancing circuit. So if I show you this BMS here, you can see that it has a circuit which is very similar to the one on this board, like so. These resistors there with the transistor to turn them on, and so on and so forth. So this is the balancing circuit. And additionally, the BMS can actually unhook the battery from the motorcycle. So through these MOSFETs passes all the current, and it can turn it off. And it will turn it off in case the battery is over discharged. So if the voltage per cell drops below 2 volts, it will unhook the battery, and it has overcharge protection. If the voltage on the cell goes above 3.75, it will unhook the battery, which is nice. It says that it's rated at continuous current of 50 amps, but it can handle a 200 amps current for a short period of time without trouble. And they say that if you put a heatsink on it, it will handle, I believe, 80 amps here of continuous current, and it has a short circuit protection. I don't know how that works. If say 500 amps is the short circuit current for half a second. That's a lot of energy. So this, as I said, I have 2 of these BMSs. This one is purchased from eBay. This was the first version that I've got, and there is at least one problem, which is a pretty big one in my opinion for this BMS. There is a balancing lead in here, which I desoldered, and the way the connector is set up when you get the board, it's actually reverse of what the batteries have. So the wires are pretty much in the inverse order, and the negative is where the positive should be, and so on. And actually, it's an interesting story. Actually, there are markings here, and the markings are correct. They correspond to what the board should accept, but they're they're not in the same order as the balancing lead on the battery has. I've seen that before I hooked it up, but for some reason accidentally I just hooked it up to this, and what happened is that a little bit of sparks but no magic smoke. So I suspected that this board would continue working, but when I hooked up the big wires, when I put the balancing lead in the correct polarity and then hooked up the big wires, what happened is that there was a trace under this red wire. You can see it there in gray. It just evaporated, this trace just disappeared, and I was able to understand what happened. And this diode, when I hooked it up, it actually passed a lot of current through it, and it became a short, and this is a short between pretty much positive and negative. So that's how it was able to pass so much current and evaporate this trace. Also, when you buy this thing, it will come with a little bit of gunk on top of this circuit. I wanted to have my own moisture protection, so I was taking this gunk out and actually damaged one of the traces. You can see a little bit of copper right there. So I had to put this black wire in here. Also, the board that I got from even the AliExpress, even though it was supposed to be the same board, identically pretty much the same, they have the same pictures and the same model numbers, but the board that I got from AliExpress had a bigger hole in there, so an 8-gauge wire would not fit through this hole, but it actually fit through the hole that they have in the board that they sell on AliExpress. So if you are deciding which board to buy, I would suggest you to go with the AliExpress one. Just make sure you desolder this one and solder it correctly when you get the board. So let's do some additional measurements and on the motorcycle, and see if we can figure out how much current is the motorcycle drawing when it starts up, and how comfortable is that for the BMS and for the battery. So this time I hooked up the multimeter a little bit differently. The positive wire goes to the positive end of the battery on the balance connector, and the negative wire from the multimeter goes on the positive of the of what motorcycle sees. So what I want to achieve is I want to see the voltage drop across this cable and this connector, then the other connector, then all the way to the battery. Because the balance lead doesn't carry any current, it pretty much sees the voltage at the battery itself, and then I compare the voltage at the positive end inside the battery to the positive that the motorcycle sees. So because this wire is an 8-gauge wire, it's not really designed to handle 200 amps for a long period of time, but it will handle 200 amps for a short period of time quite happily. I should see quite a significant voltage dropped here in this wire and these connectors. I'm not quite confident about this connector, the spade one that goes to the motorcycle terminal. I made it myself. I tried my best. So I'll probably show it in a later on video. I suspect that some rattling may generate some noise in there in the signal, but we'll see how it goes. So right now the multimeter shows 0 because there is no current flowing. The motorcycle is off. I'll just turn the ignition on. So yeah, the at 9 millivolts is drawn from the current drop when the ignition is on, and nothing else is happening. Let's try to measure what this 9 millivolt what current it actually corresponds to. So I'm turning it off. I have this awesome clamp here. Even though Dave bashes Unity on every occasion, I think this clamp is just amazing, because it allows you to measure DC current without having to unhook anything. And from what I've seen people do some measurements, it's definitely accurate enough for my particular application. So I'll switch it to 20 amps. I'll put DC in there. It says that 0.2 amps, but you have to zero it out after you put it on your wire. So I'll put this on my positive wire here. Still says 0.27, 0.26. Say no. This is 0. I don't know if you guys can see. Oh yeah, I think you can. Okay, so let's see. So it's about 11 amps, and 11 amps correspond to 9 millivolts of voltage drop. This math will allow us to compute the current when the motorcycle is actually starting. So I couldn't measure the amps that goes through the that are drawn from the battery when the motorcycle is starting, because this is rated to 100 amps, and it doesn't have a min max or inrush current measurement. So for static loads it's okay. But let's put the recording on this one and start the motorcycle. So here are our 9 millivolts. Okay, you still can see that. So the maximum drop that it saw was 0.19, 188 millivolts. So roughly 9 millivolts is 11 amps, and let's say 0.2 of a volt. So yeah, it's about 200 amps. If I take my calculator out. Let's try this experiment again to see if we get different numbers. You can see it going negative there. It's charging back the battery. So yeah, right now the maximum is a little bit more. So 0.2 of a volt voltage drop corresponds to about to 220 amps of current going through this wire. So the battery should be pretty happy with that. The BMS is rated at about 200 amps for short periods of time. So and this BMS actually is advertised as motorcycle starter battery BMS. So it's purposefully designed for this particular application. So I'm quite happy with that. So another experiment that I wanted to do is I wanted to hook up my oscilloscope to the same terminals, the positive on the battery and the positive on the motorcycle, and see the actual graph of the current that is being drawn to figure out for how much time it draws and how much current. Let me hook it up and turn it back on. So I've got my scope hooked up, and it's hooked up the same way the multimeter was. The positive terminal goes to the battery positive inside the battery through the balance lead, and the negative goes to the positive as seen by the motorcycle. So right now it sits at 0 because the motorcycle is turned off. Here I have it set up such that it has 100 millivolts per division. So with the 0.2 volt it should go up a couple of divisions up, and then the time base is half a second per division, so we should see several seconds worth of data in here. And I'll stop the multimeter once the motorcycle starts, and we'll see, you know, how the current was flowing, the rate of flow, and then we'll see how was it charging afterwards. So let's turn the ignition on. And now okay, so what's interesting here is actually that the big spike when the, I wonder if you see it well. Oh yeah. What's interesting to me here is that the big spike here goes 1, 2, 3, 4 divisions. Let's put the cursor in there. There, track, channel A, sure. Oh yeah, it says 300. Yeah, it's about actually 400 millivolts of voltage drop across the positive wire that goes from the battery to the motorcycle. Well, my previous math was that 0.2 of a volt corresponds to 200 amps. So what I see here is that it's actually pretty scary in my opinion. Is that it's actually 400 amps for a 50. I don't see the scale. For about 50 or 25 milliseconds. Let's increase the scale even more. This guy here. Oh, let's see if it has enough samples there. Dots. Oh yeah, it has plenty of samples there. The cursor. Oops. Cursor. Yeah, so there are several samples, at least at 420. So yeah, this is where I start the engine, and for about at least one division, which is 20 milliseconds, it goes much higher than the 20 to 200 millivolts, and then during the rest of the start it's about 200. So from here to all the way there, when the motorcycle starts, it's about 200. This is where the alternator kicks in and it starts charging. Let's see that cursor again. Oh, come on, track. Yeah, here it goes negative and it's charging the battery. Here it's very low. So the only concerning thing is this big spike here. It doesn't seem to trigger the short circuit protection because it's about 400 amps. I think it's pretty close to the 500 amps that the thing is supposed to protect from. But it's 500 amps for half a second, and this was 400 amps for about 20 milliseconds, which is which I guess doesn't trigger. That's an interesting piece of data. I didn't know that. I'm wondering what will happen if at any point the motorcycle has trouble starting, and I'll have to force it a little bit to see how hot the BMS will get. From my experiment so far, the BMS was ice cold. Never did I feel it even warm on the MOSFETs there. So I'm not planning to put any heatsink on. What I'm planning to do though, it would be nice to have a box. Sorry, I have to move my tripod here. It would be nice to have a case for this battery, and it was what I will definitely do is I will either conformal coat this board or put some silicone on it to protect it from moisture, because it's pretty much in open air. I didn't ride it in the rain, but I suspect if I ride it in the rain, moisture will get here. And it had some silicone on top of the balancing part. Here, as I said, it had some silicone here, but it was, you know, a small smudge. It didn't cover all of it. It was, you know, I really didn't like it. You know, if they were to conformal coat the whole thing, I would be very happy with it. Now I'll have to probably conformal coat it myself. I don't know if I'll leave these MOSFETs without coating so that I can put heatsink at a later point. Yeah, anyway, it's interesting. So, as a conclusion to this video, you know, I hope that you find this interesting. It was definitely an interesting adventure for me. I learned a lot while doing this. Probably the biggest thing that I learned is how to solder big 8-gauge wire. It's not that straightforward. I'm used to soldering little tiny pieces, and the 8-gauge wire required me to just buy a new soldering iron too, because I didn't have my 60-watt iron wasn't powerful enough. You need at least, I have a 120 butane wire, and it was okay, but you know, a 200 electric wire I think would be even better to solder the 8-gauge wire. So just as a recommendation, if you want to just save money on this thing, I actually wouldn't recommend it in retrospect, because at the end of the day I ended up paying about $90 for the battery itself, $20 for the BMS, but I ordered 2 of them. It's another $40. 2 of those balancing cards, another, you know. So I ended up into the same money. If I were to design a case for this battery, and I would definitely like to have a case for it, then it would be an additional, I don't know, about $20 for the 3D printing or a custom case of some sort. But you know, it takes a lot of time, and working with these batteries is pretty, in my opinion, dangerous, because even though they have about 12 volts, they have lots of grunts, and they can, you know, burn your wires really quickly. I didn't short this battery other than the trace that evaporated, but you know, it was pretty quickly. I think it was nothing. Yeah, what I would like to know is if anyone has any of those Shorai batteries damaged, if you can open up. I would like to know if there is a full BMS in there, and I actually suspect there isn't, because they recommend you to use the charger with a balancing lead, and as far as I understand, there is a balancing port on the Shorai battery. So I suspect that if you have a you know, good balancing circuit on the BMS, you wouldn't need the advanced charger. You know, hopefully the charger, the normal charger itself, just, you know, put a 14.2 volts on your lithium iron phosphate battery, and it will be all fine. The balancing circuit should handle that. Also, there was an interesting part of the of my setup, that I deliberately brought the battery out of balance to see how the balancing circuit works, and because the curve of the discharge level of the battery versus voltage for the lithium iron phosphate is pretty flat. That's why a very slight drop in voltage between the cells can translate into a huge drop into a huge difference in the capacity. So in my particular case, what was happening is that all the cells were at 3.4 volts, and one was at 3.35 volts, and that 0.05 of a volt difference, what actually translated to, I figured out later, it translated to about half. So the cell that had 3.35 was about half as charged as the ones that had 3.4 volts. And this was, I actually rode with the battery like that at least 2 times, and I discovered it accidentally that it's such a huge problem because the balancing circuit couldn't handle 4 amp hours worth of difference. It discharges, the balancing circuit discharges at like 15 or 30 or 60 milliamps, so it will need lots and lots of hours to be able to bring such an unbalanced battery back into balance. And in my particular case, I discovered it by accident. But when I measured it, the cells that were charged, they were at like 3.8 volts. Oh no, it probably was the other way around. One of the cells was higher and the other one's lower. Because I remember there was one cell at 3.8 volts and the other ones were at much lower, like 3.4. So when the other cells were full, the cell that had twice as much was like over and above. I think the BMS protected the battery because it disconnects the battery, but it still allowed the cell voltage to go up to 3.8, which is in unsafe territory for the lithium iron phosphate. 3.65, it's very comfortable. 3.75 is what the BMS is supposed to protect it from. At 3.75, it's supposed to unhook the battery, but I've seen 3.8 on that cell when the motorcycle was running. So. Yeah, beware of that. Don't do anything stupid like that. Keep your battery balanced. And I would suggest you to use a hobby balancing charger before you wire all the things together. I'll probably show another video of how I hooked up the battery to the motorcycle terminals, because it wasn't as straightforward. I just had to make my own spade connectors, copper spade connectors. Anyway, thanks for watching. If you have constructive feedback or some other experiments that you want me to run, please leave any comments, and I'll try to answer pretty much all of them. Thank you.